What's going on, YouTube? Welcome back to another video, and in today's video we'll be starting our technical interview preparation series. Specifically, we'll be going over the linked list in this video and how can we approach linked list problems in technical interviews. Okay, so I'm not expecting you to be a linked list master. I'm going to dive into a little bit about what linked lists are, some common techniques, and then we'll look at our Leetcode problem, which will apply what we've learned. Okay, so let's get right into it. Technical interview prep 1, linked list. So what are linked lists? Well, linked list we can imagine as a data structure, or a node as we call it, which contains two things. It contains data. This data could be anything. It could be an int, it could be a string, a double, whatever data type you could think of. And also it contains a reference to the next node. Okay, so a piece of data, and a reference to the next node. So that's why it's a linked list, right? We have a node, it points to the next node. We have this node, it points to the next node, okay? They're linked together, all right? So what does this kind of look like? Let's start with the basic singly linked list. So a few things I want you to notice, right? Again, we have the data, which is here an int 5, and then we have a reference to the next node. And this node contains the data 10, the integer 10, and a reference to the next node. Again, an int 15 and a reference to the next node. Now I want you to notice this last node. This node here, 20, well, this node contains the value 20, but its next reference, it's not pointing to anything. So the last item in a singly linked list is going to point, its next reference is going to point to null or none. So that's how we can tell that the linked list is done. That's how we can tell we've reached the end of the linked list, because this last element, its next reference, will be none or null. I also want you to notice that we do have something called a head node. Now, what is this? This allows us to know where we're starting the linked list. The head node is always going to point to the beginning of the linked list. And so in this case, the head node is going to point to the node 5, which contains 5. And that's how we can sort of identify where we're beginning a linked list if we want to traverse the linked list or do whatever operation we want. And notice this is called a singly linked list. What does that mean? Well, that just means that we're going in one direction. We're going from the beginning to the end, and there's no way we can go back. We can't access a previous element. We're just going one way. All right. There's also something called a doubly linked list. And the difference between this and a singly linked list is that a doubly linked list, you can go back and forth. You can go forward in the linked list, and you can also go backwards in the linked list. So in addition to having a reference to the next node in the list, a doubly linked list will also have a reference to the previous node in the linked list. So again, if we start at the beginning, the node with the element 5, its next reference is going to be the node with the element 10. And its previous reference, because it's the first element in the list, is going to be null or none. And then again, 10's next reference is the node containing 15, and its previous reference is the node containing 5. And if we just skip to the last element in the linked list, 20, the node containing 20, its previous reference is going to be the node containing 15. And just like a singly linked list, its next reference is going to be null or none, since it's the last item in the linked list. Sometimes you might have something called a tail. Sometimes we have the head node that denotes the beginning of the linked list. We might have a tail that denotes the end of a linked list. So if we want to do operations starting at the end of the linked list, like adding or removing an element, then we might have a tail which indicates, okay, I can start at the end of the linked list and just add or delete an item from the end. Now this last one is pretty interesting. It's called a circular linked list. It is not too common, but it is kind of interesting when we talk about the concept of a linked list. So I noticed I talked about in a singly and a doubly linked list, the last element in the list, its next reference would be none or null. Well, in a circular linked list, there really is no end, right? There is no tail reference. So the last element in the list, which in this case based on the images, contains 20, its next reference loops all the way back to the beginning. So it's a cycle, a circular linked list, right? So no element in the list has a null or next reference, okay? So pretty cool. We're actually going to do a problem related to this, so we can kind of see some techniques that we use when solving linked list problems. So just keep a circular linked list in mind. Now, why would we use a linked list, right? You may be familiar with arrays. Why not use an array instead of a linked list? Well, they do have their pros and cons. We'll start with arrays, right? Arrays allow for random access. So if we know the index of an element in an array, we can just instantly get that element just based on the index. So very fast access to elements in an array, given the index. Cache locality. So if we think in an array, we think about elements grouped together in memory, right? So because our elements in an array are right next to each other in memory, it's very easy to access them, and it speeds up operations. The cons of an array: slow insertion / deletion. So if we want to insert an element in an array, just imagine we want to insert at the end of an array, we have to traverse the entire array and then insert that element. Same thing with deleting an element. If it's the last element in a list and we want to delete it, we're going to have to traverse the entire array. An array also has a fixed size, right? So we can't really add an element to an array because we're given this fixed array in memory and we can't really add on to it. That's one of the cons of an array, as opposed to a linked list where we can add and remove elements. All right, linked lists also have fast insertion / deletion, specifically when we're talking about adding to the beginning of a linked list, right? No matter what linked list we're working with, we're always going to have a head reference. So if we have the reference to the head node, we can always, no matter how big the list is, we can insert / delete at the head node at constant time. And depending if we have a doubly linked list, for example, we may also be able to do this at the end of the linked list as well. The cons of a linked list is that it is slow to search for elements, right? We don't have an index. We don't know exactly where each element is in memory. So we want to find an element, we do have to traverse the linked list all the way through. All right. So one of the big things when we're doing technical interviews or just any type of data structure problem is optimization. And a big part of that is Big O. So I do have a video on Big O. I'm not going to do a deep dive into Big O in this video, but you can check out my video. You can check out other resources online. I'll probably do another video. But this is basically the runtime worst case scenario of our program. So for linked list, if you want to access an element, I just talked about it. If we have an element, worst case scenario, at the end of the linked list, we're going to have to traverse the linked list one by one, going through each element. And that's going to take O of n. So as the size of the list grows, the longer it's going to take to run this program to access an element. Now, same thing for adding / removing elements. Given a singly linked list, if we want to add an element or remove an element at the end of a linked list, we're going to have to traverse the linked list one by one until we get to the end. And again, this is going to grow linearly. So the bigger the linked list, the longer it's going to take for our program to run. Now, adding / removing from the beginning of a linked list, I kind of just talked about it, but if you want to add an element to the beginning, if you can just imagine, no matter how big the list is, we're always going to have a head node. And this head node is going to have a next reference to this other node, right? So if we want to add an element, we're just going to insert the element in between those two elements. So in between the head nodes, and the head node is now pointing to this new element. And this new element is now pointing to the reference that the head node was pointing to, if that makes sense. No matter how big the list is, this is always going to be like 2 steps. It's always going to be like 2 or 3 steps to add an element to the beginning of the list. So that's why it's O of 1. It's constant. It doesn't depend on the size of the linked list. Bonus, if we have a doubly linked list, if we want to add / remove from the end, this is also going to be O of 1, right? Because we're going to have a tail reference. We can move backwards in the linked list as well. It's essentially the same thing as adding to the beginning of the linked list, since we can go not only forward in the linked list, but backwards in the linked list. That is a pretty brief rundown on linked list and its operations and whatnot. Now I'm going to talk briefly about some common techniques that we will use to solve a problem involving linked list. So one is a temp / dummy node. I say temp node. So this is kind of, as I have here, useful for returning modified linked list. So typically what we'll do is we'll create a temp node, and this is just going to point to the head node. And instead of modifying the head node and traversing with the head node, we're going to traverse with this temp node. So that way we're not modifying the head node and doing things that we don't want to do, specifically when talking about edge cases. The next is a 2-pointer technique. As I have here, we have a fast pointer and we have a slow pointer. So really, if we imagine it, I do have a diagram as well. If I have a fast pointer, is basically exactly what the name implies. The fast pointer is going to move faster than the slow pointer when traversing a list. So the fast pointer might move 2 elements at a time, while the slow pointer moves 1 element at a time. And we're actually going to use this technique in a problem that we're about to do. So it may not make sense, why would we ever use a 2-pointer technique? Well, we're actually going to do a problem right now. We're not going to do a temp/dummy node problem, but I will probably link some problems in the descriptions for you to practice that. It's a pretty common technique that you'll use in a linked list problem. But the problem we're using today, we'll use 2 pointers, okay? So without further ado, let us practice. So we're going to do a linked list cycle problem, detecting a cycle in a linked list. And if you remember before, I talked about what a circular linked list is. Well, now we're going to detect if a linked list is circular, okay? All right, so this linked list cycle problem is going to give us a description. Given the head of a linked list, determine if the linked list has a cycle in it. There's a cycle in a linked list if there's some node in the list that can be reached again by continuously following the next pointer. Internally, pause or position is used to denote the index of the node that tail's next pointer is connected to. Note that position is not passed as a parameter, and it wants us to return true if there's a cycle in the linked list, and if not, return false. Now it's going to give us some examples here of what a cycle would look like and what it's supposed to return. So obviously here at the end of the linked list, there's a cycle that circles back to the node containing 2, and so this will return true. And again, this example 2, it has a cycle with just 2 elements in the linked list, and the last one is just 1 element, so it's going to return false because there's no cycle. It also gives us some constraints. So position is -1 or a valid index in the linked list. It's going to give us some how large the linked list can be and how large the values in the linked list can be. So when we're thinking about this problem, I'm always going to try to understand what the problem is asking us to do. So from a basic concept, we know what a circular linked list is. It gives us some example of what it would look like. And we got to figure out what we're trying to do here. So we're trying to detect if a linked list has a cycle in it, and we're going to return true if it does. Well, can the linked list be empty? We can start asking questions about, can the linked list be empty? It already gave us some constraints, but say we didn't have these constraints, we could ask the interviewer, are there any time constraints, space constraints, whatnot. We know that a linked list, it can not have a cycle. If it doesn't have a cycle, then it's going to return false. Boom. Just thinking out loud, expressing our thought process to the interviewer, okay? So once we kind of have an understanding of the problem, we can try and think of ways we can solve this problem, okay? So my first thought is that, I talked about it earlier in the video. If we have a cycle, right, that means that no element in the list has a next reference that is none or null. And we can try to think about what are ways we can detect if that's the case, right? How can we determine if there's no next or null reference in the linked list? Well, we can use a 2-pointer technique or a 2-pointer solution, right? The slow and fast pointers technique. So if I have a slow and a fast pointer, both starting at the beginning of the list, if I have a fast pointer that moves, say, 2 elements at a time and a slow pointer that moves 1 element at a time, well, eventually, if there is a cycle, the fast pointer is going to catch up to the slow pointer, right? It's just inevitable because there is no next reference. The linked list doesn't end. So we're incrementing one pointer faster than the other. If it's a cycle, it's going to catch up to that slow pointer. If there is no cycle, well then eventually the fast pointer its next reference is going to be none, right? So that would detect the end of the linked list. So I hope that kind of makes sense there. So if there is a cycle, well, then the fast pointer is going to catch up to the slow pointer. If there's not a cycle, well, then the fast pointer's next reference is eventually going to be done. So let's tie those together. So let's start off by declaring a slow and a fast pointer. Again, we want to start at the beginning of the linked list. So we're not really modifying the linked list. We're just checking if it has a slow and fast pointer. So we don't really need to have a temp node. I'll do slow equals head, fast equals head. And again, the head pointer is pointing to the first element in the linked list. All right. Now, let's go back to the point where if the fast pointer's next reference is null or none, then there is not a cycle in the linked list, right? So to do that, we can just do a while loop to check if the fast pointer is ever null or none, or if the fast's next pointer is ever null or none. So while fast and fast.next. So this is saying while fast is not none, and while fast.next is not none. As long as we detect that there is a cycle in the linked list, we're gonna go through this while loop, okay? Next we're gonna do is we're gonna increment these slow and fast pointers accordingly. So I want the slow pointer to go one element at a time. So that way it really is slow, is moving slower than the fast pointer. So slow equals slow.next. So while the fast pointer is not none, we're just gonna traverse this linked list with the slow pointer one at a time. And again, we also want to move the fast pointer. So if the slow pointer is moving one element at a time, is moving to its next reference, the fast pointer I want to move at 2 elements at a time. So fast is going to be its next pointer's next pointer, right? That's 2 elements. So fast equals fast.next. All right, so this slow pointer is going to move 1 element at a time. This fast pointer is going to move 2 elements at a time. That way the fast pointer really is moving at a faster rate than the slow pointer. Really, we're almost done here actually. So we just want to check if the fast pointer and the slow pointer ever, are equal to each other. So that will, if they are, then that means that we do have a cycle, right? That means the fast pointer caught up to the slow pointer. So if fast pointer equals the slow pointer, then we're just going to return true. So there is a cycle because the fast pointer caught up. Now, lastly, if the fast pointer or the fast.next pointer is ever null or none, that means that we're going to exit out of this while loop. This means that we do not have a cycle, right? So that means the linked list ends and we can just return false. All right. So I hope that makes sense. I hope I explained that pretty well. If you have any questions, you can always, ask me in the comments. What did I mean by that? Why are we doing it this way? But this should work just well. Just double checking. I think it looks good to me, so I'm just gonna run this. And we do pass all the preliminary test cases, so that's good, right? True, good, and good. All right. And I'm just gonna submit this just to make sure we pass everything. It should actually tell us the runtime here, right? So beats 85%, whatever. This should be O of n runtime because we do have to traverse the entire linked list, right? Space complexity, it should be O of 1 or constant because we're only creating 2 pointers no matter how big the linked list is. That's about it in terms of linked list. I hope I introduced some new strategies that you didn't know about, some ways that we can think about solving a problem when it comes to an interview. And I hope I was helpful in this video. All right. Thank you all for watching. I hope you learned something and I hope to see you in the next one. Take it easy.